For this problem, we have a 70 kilogram person pushing a 10 kilogram cart with a net force of 12 newtons. First thing I want to do is create a free body diagram. I'm actually going to create the free body diagram for the cart. And the cart is experiencing an applied force of 12 newtons. Then it also has some sort of force due to gravity, and that would be 10 kilograms times 9.8 meters per second squared. Okay, from our F equals ma relationship. The first question asks, what's the acceleration of the cart? It doesn't matter what the mass of the person is at this point. It may not matter what the mass of the person is at all in this problem. So the acceleration of the cart, we need the net force that's being applied, or the force being applied, and we're assuming friction is negligible. So F equals ma. The force being applied is 12 newtons. The mass is 10 kilograms, and we're looking for the acceleration. So solving for A, I get 12 divided by 10, 1.2 meters per second squared. The second part of the problem asks, assuming the cart was initially at rest, how fast is the cart moving after 3 seconds? So we know our initial velocity is 0 meters per second. We are looking for our final velocity. We know our acceleration is 1.2 meters per second squared, and our time is 3 seconds. So to solve for the final velocity here, we're going to use the equation that the final velocity equals the initial velocity plus acceleration times time. We are looking for that final velocity. We know the initial velocity is 0. The acceleration is 1.2 meters per second squared. The time is 3 seconds. So 1.2 times 3 is 3.6 meters per second. That'll be the velocity of the cart after 3 seconds. When you're pushing a cart in the grocery store, while you're applying the force, the cart's accelerating. To keep the cart going, you would not be applying a net force. So the force that you would be pushing the cart with would just be enough to compensate for friction. Otherwise, you would be pushing the cart and you would continue to accelerate and accelerate and accelerate, which would make other people at the grocery store very nervous. You push the cart with a applied force to get it to the speed you want, and then you just maintain that speed with a force equal to the force of friction slowing the cart down. The last part of the problem is, what is the weight of the cart? The weight of the cart is going to be equal to the mass times the acceleration due to gravity. Sometimes people say mg, g for the acceleration due to gravity. Sometimes people say a sub g for acceleration due to gravity. We've got 10 kilograms times 9.8 meters per second squared. So that's going to equal 98 newtons. I'm bringing this back up because this slide is about Newton's second law, but also I just want to talk briefly about weight versus mass. The mass of the cart, whether or not it's on Earth or on the moon, is always going to be 10 kilograms. That's constant. The weight of the cart depends on this acceleration due to gravity. So the weight of the cart is 98 newtons on Earth. It would be about 1/6 that if we were on the moon. So remember, mass is always the same no matter where in the universe you are, but weight can be different.